let's get started with the heat transfer application project. I'm Dijan Sun, and my teammate is Jerome. He's taking tests right now, so I'm recording this video. And our team projects the computer heat dissipation testing. So, main purpose is to test the convection coefficient of water cooling system for PC. Also, calculate heat flux during the computer working process for CPUs, and also to test the effect of heat dissipation on CPU from the other components. So let's dive into the model right here. So this is an actual computer. This one is CPU. It has a water cooling system attached on it. This is a GPU. It has an internal wind cooler, surface convection, and the fans provides limited convection for motherboard and RAM right here, and disk should be somewhere hidden right here. And so this model is kind of complex to provide the modeling and simulating, so we identified these components to be the majority of heat consumption and heat dissipation requirement for the entire things. So we come up with a simplified model. It's very close to this one, just looks easier for both. This one is CPU, GPU, RAM, disk, and motherboard. So for the boundary conditions, only the CPU is served as the tested component. So this one should be an heat flux calculated by the area and the power and the maximum power. Before testing, we measure some parameters, especially temperature, just temperature, about these components because we're holding all the others and the fluids, including air and water, to be a constant temperature. So it's more convenient to test the heat transfer rate of this one. So here is the testing value. The method of testing is like, this is my laptop. My teammate is testing this value from his computer, and temperatures will pop up in here. My laptops use wind cooling, so you can see CPU temperature usually rush to 80s or 90s. It's terrible. And these are the values after testing. It came out from his computer and monitor, and also the thermal thermometer. So let's introduce the boundary conditions of each component. So first, CPU is a heat generating source, and it's tested. So we're using flux instead of temperature. Also, this surface is attached to the water cooler, so there is a convective surface as well. And for GPU, one side, this side is dissipating heat because actually there's only one board right here generating heat. The other side is a huge cooler. So this one is said to be one side of constant temperature and two sides of convective surface. Also for RAM and disk, these two components are generating heat, but naturally temperature is high due to the poor heat dissipation of itself. So it's still said to be a constant temperature with a poorer convective surface, as well as motherboard. And also last one, motherboard doesn't have any heat generating source that can be considered comparing to with these guys. So it's not generating heat, it's just a convective surface. That's the model of the project. And let's go to the demonstration part. So this is the SolidWorks model we generated. The result has been already passed out here. There's a bar column targeting the temperature. So what we did for testing is to assume some values at first. And temperature is a temperature on the words. It might be kind of hard to read, but you can just look at here, look at an image. The temperature tested, and the convection heat transfer coefficient for GPU and motherboard. I'm assuming this value, and I will approve it's not necessary to assume an accurate value. And this one is the output value. We change this value until the surface temperature of the CPU reach the target. So right here, this value has already has a set of outcome from common settings at 20 watts per meter square Kelvin for motherboard, 90 for a stronger one, so it's 90 for GPU. I'm going to change it to high value, extremely high value, like 500 for both, and holds the value for CPU the constant and see the result. So green bar up here, green a little bit yellow up here. So the result should be the same as this one. It's very close to 336, 337 Kelvin. And after conversion, it's around 64 Celsius. To save time, I'll skip the one with only 1 watt per meter square Kelvin. So I'll dive into the change of temperature. Change it back first. So I'm holding this constant as an initial value. I'm going to change all these values. I'll add 20 per each, 20 Celsius per component. And green bar. You can see it's green. 3, between 4 and 9. 5 and 6. Still close. Still close to this value. It's close to 9. But actually it doesn't have too much changes. So the outcome is the impact from the other components to the surface temperature of CPU can be neglected. So we got our validation process. The only thing we need to do is to calculate the surface temperature of this one and the surface condition, like the convection. Calculate the convection heat transfer coefficient of the surface using this equation. Move it to here, and we'll get the value. So the result is around 4100, a little bit smaller than the tested value. Well, this outcome is acceptable for us for the stage of the simulation because actually this model is dissipating more heat. It should dissipate more heat because each time I change the values right here, it should have a 1 or 2 degrees of changes as uncertainties when I change this value. So actually, there are more than one heat generating source. So this value is supposed to be larger than the ideal value calculated. So I can say this result is within the anticipation, and it follows the prediction as a mainstream. It puts us someplace where it should be in general. So that's our application project. To conclude this, we do this project because this value, heat transfer coefficient, is hidden. The manufacturer didn't even provide reference or something. It doesn't provide anything relating to this. The only parameters we could find is the sound and RPM for the fans. But this is a factor or the directly related value to the heat dissipation efficiency. We're testing this so we could have a better choice when we purchase another computer, and we can compare different water cooling systems of different bands and scales because the price is different. Sometimes you might find out they might have a different difference. They might have a huge difference in the price, but you might have a similar heat transfer coefficient because this value is hidden for all of them. The manufacturer wants to post this, so we're going to test it. It's beneficial for us, especially the customers. And I think that's it for the demonstration part and the presentation. Thanks for listening and watching.